So good morning everyone. What I'm going to talk today is some recent work that I have started to do on two-dimensional turbulence with binary mixture and polymer additives, and there is a story which connects the two systems, the one of binary mixture and polymer additives, and I hope to convey the message that what are the similarities and differences in these two systems. However, the final phenomena that you would see would be very similar. There would be subtle differences, so we'll see as we go along. And this work was done in collaboration with Rahul and Nairita from IISc, and Anupam, who is presently at postdoc in Tor Vergata, Rome, and was earlier again a PhD student with Rahul. So let's just get started with the first part of the talk, which is two-dimensional turbulence in a symmetric binary mixture, and why one should even worry about it. So that's the first starting point. So one should worry about turbulence in symmetric binary mixtures for a simple reason. That if you want to form an emulsion, okay, the easiest way to form an emulsion is you take a binary mixture and stir it up, and then you would form an emulsion, and then later on you can stabilize this emulsion by adding surfactants or other things, and then you will get a stable emulsion. However, when you are forming this emulsion, an obvious question arises that what is the size distribution of droplets inside this distribution, what is the smallest structure that you would form in this emulsion, and those are the questions that interest me, and the talk would be about, can I predict these structures, the size of these structures in a theoretical way, and then compare it with simulations, and whether what I am saying, whether it holds anything in three-dimensional turbulence or not. So we'll see as we go along. So this is the experiment that one would typically do. You would have two oils, and what you can do in your kitchen is you put in a stirrer and just stir it up, and then you would get an emulsion, and this emulsion is consistent of constituents of and also the physics of turbulence, okay. And as a test system, what I am going to take is two-dimensional turbulence, which is far away from the three-dimensional turbulence which happens in this system, but as we go along I will point out the similarities between the two. So okay, let's first get started of how I am going to model the phase separating emulsion, okay. So the way I am going to model is the standard 5-4 theory of phase separation, the spinodal decomposition. And so the picture is this, that if you have on the x-axis concentration or the order parameter, whichever thing you like, and if you are above a certain temperature Tc, the system remains well mixed. But if you quench it below the critical temperature, the system spontaneously phase separates into A-rich and B-rich phases, and this physics you can very easily do or simulate using a Cahn-Hilliard equation, and here is a realization of three-dimensional phase separation done using a Lattice-Boltzmann simulation, where you started from a well-mixed state, and this well-mixed state spontaneously phase separates into A-rich and B-rich phases. So at the outset, but let me point out that in my studies I am going to completely ignore thermal noise, which is an essential ingredient in most of the theories of phase separation. So this will be in the sense of mean field, okay. And here the phase separation, the initial mixed state, you already see that I initialize at the initial set, I give it certain perturbations so that the phase separation is initiated. Okay, now the equations that give, or which would tell you how the phase separation proceeds, is actually, because we are interested in liquid systems, is actually Navier-Stokes coupled with the Cahn-Hilliard equation. And so this is your standard Cahn-Hilliard equation with a free energy function, which is a 5/4 form. The last term gives you the cost to maintain the surfaces, or this is a coupled system. There is a back reaction of the order parameter field onto the Navier-Stokes, which contribute towards the surface tension, okay. Now these are the set of equations that you have, and then you can ask yourself that if you take a realistic liquid-liquid binary mixture system, how does this course thing proceed? So that was the question. Actually it's not what I answered, but that has been looked up from last 30-40 years by many people. The first of the theories were by Lifshitz and Schleicher, which was actually for a metal binary mixture system, and where he actually showed that what you can, based on based on nucleation and coagulation, that you would expect a length scale of these domains growing as t to the power 1/3. Okay. Now this you can also predict by just doing a dimensional analysis. You can just compare the dimensions of 1/t with the dimensions of the chemical potential, and you will straight away get that the length scale grows as t raised to 1/3. You won't be able to predict the prefactor, but this thing you will get straight away. Later on in Sigia came up with the idea that why stop here? If I have a length scale which is growing, I can come up with a Reynolds number, which is length scale into the speed at which the length scale is growing, divided by viscosity. I have a Reynolds number, and so at later times what should happen is that the viscous forces should balance the surface tension forces, and if you do that, you get a length scale which grows linearly in time. And then people said that, oh, why stop even over there? Because I have a Reynolds number, that can keep on growing. More recently in 2000, Kendon came up with the idea that I can even come up with a balance of inertial terms with the surface tension term, and then I'll get a length scale which grows as t raised to 2/3. I'd like to point out, in most realistic systems, most experimental systems, what you get is t raised to 1/3 and t log. I haven't seen a single experimental system where you observe t raised to 2/3. Okay, so this is about what happens to the coarsening when it proceeds in the normal way. Now the question is, what would happen if I switch on turbulence in this system? And if I switch on turbulence, at least in the experiment, this kitchen experiment that we observed earlier, what I should expect is that the coarsening would stop at one of these intermediate scales. The question is, can I predict what is this length scale where it stops? So just before we go dig deeper into how turbulence and coarsening would interact, let's just see this basic idea of turbulence and what is the basic idea of coarsening. So turbulence is, all of us know, is an effective mixer. One could describe, very vaguely this effective mixing in terms of some kind of a eddy diffusivity. If you are thinking of a passive scalar, it breaks larger blobs into smaller ones, and there is a spectral transfer of energy either from large scale to small scales in 3D turbulence, or from small scale to large scales in 2D turbulence. But the point is that this energy flux remains constant when you are in either of the two regimes. On the other hand, coarsening is exactly opposite process. You are demixing, you have small fluctuations which grow, become larger fluctuations, right? If you look at, it proceeds with different growth law, but the important point is that there is a spectral transfer of concentration flux from small scale towards the larger scale, okay? So that's exactly opposite to what turbulence would do. So one would, whatever you saw, 2D also concentration is, 2D also coarsening is the same thing. 2D coarsening.
What I'm saying is similar to energy transfer.
No, but in 2D, if you think of energy transfer, yes. But what I'm saying is that if you put a blob of concentration inside a 2D fluid, although the energy flux is inverse, it still breaks up in. So the concentration, the eddy diffusivity is still in. Okay. So now the point is that what happens when you compete these two things and how you go about it. So okay, the simplest thing you can do is you take these equations, put it on a computer and see what it does, and then try to see if you can do any predictions which match with, or can you predict what you observe in your simulation. So yeah.
Why are you taking the position of both phi and phi to be the same?
No, it's not same. It's -1 plus. Oh, that's a choice because I want order parameter to be +1 -1, and later on we will see that has a consequence on something. But so I'll come up with the effective temperature, but that's it for a later time. Okay. So and now what I'm going to assume is further more simplifications, which my claim would be won't affect any of the reality, but that needs to be checked. I'm going to assume that the two liquids are same density, they are same viscosity. I'm going to assume periodic boundaries, and the only thing that distinguishes two liquids is the surface tension. So there is a surface which distinguishes between the two liquids. However, for everything else, it's the same. Now, whenever you do a theory of fluids, the first thing you look for are what are the conservation laws in this system, right? Now, if you are from 3D turbulence, you straight away realize that the conservation laws are energy and helicity. On the other hand, if you look at two-dimensional turbulence, what you find is that the energy laws are, so the conservation laws are energy and all moments of vorticity, okay? However, if you look at this system, even in 2D or 3D, what you realize is that there is only one conservation law. The conservation law is that the total energy of the system, which is the sum of the kinetic energy of the fluid plus the free energy, that is conserved in the limit of viscosity going to 0 and this diffusion coefficient or the mobility going to 0. Okay, and that can be written or proved straight away like this, that the sum of kinetic energy plus the free energy is nothing but viscous dissipation plus dissipation because of the chemical potential plus the amount of energy that you are injecting into the system, and of course these two terms, because they are dissipation, they would be negative. So in the steady state, what you expect is that the energy injection balances the viscous dissipation and the dissipation because of the chemical potential that is present in the system. And unlike the pure fluid counterpart, there are no vorticity conservation laws that you can straight away guess in the system. However, for each of the two phases, you would expect that the vorticity conservation laws are still valid. So now just, as I said, I would be working in 2D turbulence. So 2D turbulence is a field which was somehow, these two guys, Krikman and Batchelor, and also there was Leith, who first came up with the idea of that, or fact that 2D turbulence is different than 3D turbulence, in the sense that in 3D turbulence you only have the forward cascade of energy. However, in 2D turbulence, if you force at intermediate wave numbers, then you have an inverse cascade of energy. A physical realization of that would be the smaller vortices would merge and form a larger vortex, and you have a forward cascade of entropy, which entropy is nothing but a vorticity squared integrated over the volume. What I would be interested in is, because I want to make analogy with 3D turbulence, is this inverse cascade regime where you have a spectral slope which is same as 3D turbulence. However, the energy flux is in exactly the opposite direction. So that would give you some dissimilarities with 3D turbulence, but that's the same spectral slope would give you some, allow you to make predictions which would also go over to 3D turbulence. Okay, and we will see what are those predictions. So now what I want to do is, I want to start with a phase separated system. Okay, so imagine that you have this kind of picture for velocity, and let's say I draw a straight line in between, and on the left hand side I made all black, which was one oil, on the right it was all white, which was the second oil, and I want to switch on, I want to see how this interface behaves when I switch on turbulence, and what is the effect of the fact that you have this additional interface on the energy cascade. Does it anyways change? Okay, and can you predict what changes would happen here? And my claim is, it is going to change how the energy flux takes place in the inverse cascade. Actually, it's going to change it in a very interesting way, and I'll come to it in a moment. So again, I mean, what people had earlier looked at, and this was known, so this is an earlier work by Guido's group, where they showed that if you take a phase separating binary mixture and put it in two-dimensional turbulence, then there are two regimes. One regime is where this, when you look at this system, what you found is there are domains of A-rich and B-rich phases, okay, which are getting mixed in presence of turbulence. Okay, and what you find is that there are sometimes the domains are larger than the forcing scales, and then there are other cases where domains, so some cases where domains are larger than the forcing scale, and other places where domains are smaller than the forcing scale. It's the same thing as done in our simulations. And what they were able to show is that what happens when you have domains which are smaller than the forcing scale. So their paper ended by saying that there is no clear picture of whether we can predict what would happen if the domains are larger than the forcing scale. That was not clear. And what was also not clear is that whether anything happens to the energy transfer. Okay, it was not at all clear. So they said that, okay, it happens like this, that you form smaller domains, and then they had a prediction for the domain size, but this was with the idea that the energy transfer and other things remain same. I mean, at least they didn't talk about what happens in reality. So let's go ahead and let's see what happens now when we do our thing. So first thing you realize is that, okay, first thing that I like to point out, that I will be always talking of the regime where the domains that you are forming are larger than the forcing scale that you have. Okay, so let's first think of what happens when you just look from this kind of a picture. So imagine that you start with a system where you have one single domain which is separating two fluids, and you switch on turbulence. If the turbulence intensity is small or the surface tension is large, the best the turbulence can do to this interface is just undulate a bit. So if you measure what is the size of the domain, you would see that it's more or less half the domain size, and it fluctuates around the same value. Now when you reduce the surface tension, you can deform the interfaces much more. So you'll form domains of smaller size, So as you are going on reducing the surface tension or increasing this non-dimensional Weber number, which is the ratio of, which is inverse surface tension, you see that the domain size keeps on reducing. Now again, I mean, this anyone would have guessed, and there is, that's not a surprise. The question is, can you predict what is the size of this domain, and can you predict it in a way that you can then compare it with experiments, okay? So if you want to predict what is the size of the domains, you should go back to the theory of turbulence, and with a mean field kind of a picture, what we have is, we have an inverse cascade of energy, and what we have are domains which are living in this inverse cascade of energy. So at any point, if I ask what is the velocity fluctuation across any of the domain, that would go as k raised to minus 5/3 or r raised to power 2/3, and then you know you can break or not by saying that, well, if a domain is going to break, then the shear across the domain should exceed the surface tension contribution, the forces because of the surface tension. So which just means that all I need to balance is rho times delta u square with the surface tension contribution, which is just sigma over r, and that is what is done. So what I do is I look at again this non-dimensional Weber number, which if you look at it, it's nothing but the ratio of inertial forces to surface tension forces. So rho u square is inertia, surface tension is sigma over r, the pressure term, and if I balance these two terms, so let's say I say, oh, around Weber number 1, if the Weber number is greater than 1, the domain is going to break. If it's less than 1, it's not going to break. So then it's all nothing but that rho u square balances sigma over r. Now when you want to put in for u square is nothing but velocity fluctuation across this domain, and for that you just put in what you get from Kolmogorov's prediction, that is across the domain delta u square would go as size of the domain raised to 2/3 and energy dissipation rate raised to 2/3. You plug it in, you get the maximum domain size, okay, which is based of course on the energy injection rate and inverse of surface tension with some power. The question is whether this is right or wrong. Now in earlier experiments with Shell, Clay in 1940s had checked a similar problem, and that problem was, let's say I have a wind tunnel, a turbulent wind tunnel, and I have a droplet going through this wind tunnel, whether that droplet is going to break under turbulent fluctuations or not. And you can just guess that the calculations are going to be exactly same. There is nothing new over there. The only thing is that the pre-factor in my case might be different because I also have coagulation events taking place, whereas his question was, if I have a droplet going through a turbulent stream, whether it's going to break or not. So there is just a breakup event. And what he showed is that if it measures droplet diameter versus the energy dissipation rate, then over 1, so it's 2, 4, 6, 8, around 8 decades, the prediction works very well. Okay, so this is the black curve, the black line is the prediction from this theory which was given by Hinz, and the red, the dots are the experimental data. Okay, now the question is, because all these predictions are just using scaling theories, okay, there is no idea about, oh, what is the direction of flux or other things. So whether if I do the same game in my 2D turbulence, would I get back the same thing or not? And the answer is, I actually get much better things than what he got. So see the number of decades, it's roughly 2, 4, 6, 8, 10 and maybe slightly more than 10. So around 10 decades what I have done is varied surface tension and plotted it with the, the size of the domains, and you see across 10 decades I get a very nice prediction. Okay, so which means that the size of the domains is completely, I can predict it, and it's based on the simple scaling argument that I invoked from Hinz. Okay, now that's great, but that you would have said that, so what's the new thing? If I was doing 3D turbulence, I would have observed the same. If I do 2D turbulence, if the spectral slope is same, I observe the same. So does 2D turbulence bring in something new? And the new thing is the following, that if you are doing 2D turbulence, then you can ask yourself the following question. In this picture, there is a inverse cascade of energy towards the large scales. Now you ask yourself, what stops this inverse cascade of energy? Now if you do a bigger and bigger domain, you would see that this inverse cascade goes to larger and larger length scales. So in a realistic system, the thing that stops this inverse flux cascade of energy is either presence of boundaries or the fact that whatever experiment you are doing, it's in contact with air. So again you have a sink which dissipates off this large scale energy. Now in our system, it turns out that the fact that you have domains present in the system, that acts as a natural cutoff scale. So then I would predict that if I have just one domain which is undulating, then my spectral flux should go all the way to half of the size of the box. If I have a domain which is smaller, then it should cut off at a smaller scale. This is what the picture I would have. And now the question is whether does it hold, and the answer is yes. So here is a picture of simulation of inverse cascade. So in the first case, my surface tension is largest or the Weber number is smallest, and what you see is that the energy transfer goes all the way up to the largest scale. Now as I go on reducing the surface tension, I form smaller domains, the energy cascade stops earlier, and at very small values of surface tension or very large Weber number, the energy cascade completely dies off. The inverse energy cascade completely gets truncated. Now then you can ask me that, oh, what determines where this stops? Is it same as the size of the domains that you have present in the system? And the answer is again yes. You can plot the energy flux, and here is a negative energy flux of 2D turbulence, and you see that as when I have only single domain, the energy flux go all the way up to the largest scales or the smallest wave number, but as I go on systematically increasing the Weber number, the energy flux stops or gets truncated at smaller and smaller scales, and the vertical arrows indicate the size of the domain. So for the black curve, the vertical arrow indicates the size of the length scale where the cascade is going to stop. Yes?
In some weird existing the limit. You go to the limit, the waves are smaller and smaller and smaller. You get again a signal.
You are completely right. So there is, so I am skipping that part. You are completely right that as I go on reducing the surface tension, it should go up. Yes, you are completely right. But that's one place where you have to be extremely careful with the Cahn-Hilliard description, because the interface widths start to become larger and larger, and then you are not so sure of what you are doing. So that's why I am not going into that regime, but you are completely right. That's what is going to happen. What one can then ask is that, okay, what is this? I mean, when I say this, does it have any implication on the standard spinodal decomposition picture that we had? Does the fact that you are making smaller the fact that when you have turbulence you stop the coarsening at some point, can I think of it in a way that there are two things that might be happening, the fact that I am mixing the things is like effective temperature in the system. Okay, so if I want to think in terms of effective temperature, I have to also check whether the level of this yellow and blue, whether the maximum and minimum values of concentration also change when I am doing all these things. Okay, and as that is in line with what you were also saying, eventually if it has to become completely mixed, it has to be all uniform. So is the inverse of the Weber number like a effective temperature, and can we test it? So here is a plot of the standard spinodal decomposition that you had, and as you are going on increasing the temperature, what you would have expected is that the maximum and the minimum values of concentration going on reducing. Now that this should be inverse Weber number. Now if I do look at my simulation and I plot the probability distribution of concentration normalized by the maximum probability value so that all the plots are on the same curve, you indeed see that the maximum value of the concentration keeps on shifting towards the smaller and smaller value. Now you can be more ambitious and you can start to ask that, similar to critical phenomena, can I predict how is this curve looking like? Okay, and then is it exactly one-to-one? Unfortunately, it turns out that's not the case. And so let me not go into that, but if you want we can discuss about it later. But the point is that there are similarities which indicate that the fact that you have turbulence in the system, it's as if you are increasing some kind of a effective temperature present in the system. Okay, so there are two interesting things. One is that you are increasing the temperature, and the other thing is that you are arresting the coarsening completely. Alright, so with this let me stop for the first part, which is that at least I think I have convinced you that when you have an elastic degree of freedom, namely here the surface tension which interacts with 2D turbulence, okay, and the size of the domains that you have are much larger than the size of the forcing scale, then not only you truncate the inverse flux of energy, you also have this standard picture of coarsening arrest. Now once I have done this, I would like it to compare this picture with another picture which have been very prevalent in turbulent community, is what happens in another system where again elastic forces are dominant, which is polymeric turbulence, but where the polymers themselves are much smaller than any of the sizes that are present in your turbulent system. Okay, and then the question is, what happens to the energy flux transfer over there? Is it same as in this picture, although the mechanism, the exact mechanism might be different? So let me go over to that. Hey, how much time I have? Oh, okay. So then let me go over to that. So when you are thinking of, unlike the binary mixture, which was in a very concentrated regime, you have 50-50 mixture. When I am talking of polymeric solution, the place where they are interesting is in the dilute regime. So by a dilute regime, I mean the concentration of polymers now is few parts per million. So exactly opposite regime to where I was working earlier when I was thinking of binary mixtures. Now, why these systems are interesting? These systems are interesting because they are known for drag reduction phenomena. They are known to reduce all the small scale structure, and actually Itamar has a very nice review article which discusses drag reduction in a variety of system, okay, for dilute polymeric solution. So I won't talk about these realistic systems of pipe flow, channel flow, but I will stick with the system to make comparison which was same as the last system, that what happens when I have 2D turbulence, but now in another multi-phase system which is polymer additives, and what are the things which are similar to the last thing and which are different. So again, I mean, this is something that one could test with experiments. So people have done experiments on soap films where what they find is that as you are going on increasing the polymer volume fraction, the dissipation because of polymer enhances, whereas the contribution to the dissipation because of viscosity reduces slightly. But let me ignore that and let me stick with what happens to the energy flux and the energy cascade in this system. So one thing that experiments found out was that similar to the binary mixture case, but for a completely different reason, most probably the effect of polymers also is very similar. The effect of polymers is to reduce or truncate the inverse energy cascade. So this is a real space picture. Here is the forcing scale. If you didn't have polymer, you had the standard inverse cascade of energy, now in real space showing a slope of 2/3, but the moment you added polymer, this inverse cascade got completely truncated. Now the question is, do you again observe this when you look at or do these things in your simulation, and what is the picture which would explain this phenomena? Okay. So again, I mean, if you want to model polymers, the way we go about it is to work in fields. Now we are talking of dilute polymer solutions. So the way to go about it is to write an equation for a single polymer and then to generalize it for a field. And the model that we have for a single polymer is a very simple dumbbell model, 2 beads connected by a spring with a nonlinear spring constant. This model is called a Philippi model, and this is the equation which describes how does the end-to-end vector evolves. And so this equation has 3 parts. The first part is the fact that if you have a velocity gradient across the polymer, then it would stretch the polymer. The second part is that because of the entropic forces, the polymer would like to relax to the coil state, and then there is a contribution because of the noise. So what we have then is 2D turbulence, which is shown over here. Then the polymeric system, so instead of working with a equation like this, it's what I would work with the equation which is average over the thermal noise, and which then is an equation for the conformation tensor, which is exactly the same terms as this. There are these terms which tell you about the extension of the polymer and the rotation of the polymer, and this term which tells you about the relaxation of the polymer. Now the important point is that the polymers live at this very large wave numbers. Their size is much smaller than any of the scales that you have in the turbulence, or they lie in the deep dissipation range. And now the question is much more surprising. If you have something which lies in this deep dissipation range, can it have any effect on the inverse cascade, or can it have any effect on the forward cascade? And if it has any effect, can there be a general picture which describes this full cascade phenomena? And again, I mean, the thing that we do is do a numerical simulation, and let me skip this, but let me come over here. What we find is that if you do a simulation with polymer additives, so this was again the inverse cascade, the red curve is for the pure Navier-Stokes, where you have an inverse cascade of energy and the forward cascade of entropy. And the interesting point is that the moment you added polymers and increased its concentration slightly, again the inverse energy cascade gets truncated. There is a decrease in energy transfer at intermediate scales, and at very small scale where the polymer lives, they pump in energy back into the fluid. Okay. Now the question is, what is the spectral slope here? Can we compare it with something that we know? And if you want to do that, you have to do a much higher resolution simulation. So for this we did a 16384 square simulation, where what we found out was that the inverse energy cascade is truncated indeed. This is again we observe is same, but the forward, this extra thing where the polymers are reacting back onto the fluid, you have a beautiful slope of k raised to minus 2.7, which is very similar to the slope that is observed in elastic turbulence. So I'm not sure whether it is elastic turbulence or not, but the point is it seems to be showing that in the deep dissipation range, where the velocity fluctuations are much smoother, the effect of polymers is such, or it's somehow manifesting itself in terms of the elastic turbulence. And so you have all the three regimes. The interesting part is that the polymers are sucking off energy not only from just the forward cascade, but in a non-trivial way from the inverse cascade also. Now unfortunately, I don't have a picture which was similar to the case of binary mixtures, where you could clearly say what is the length scale at which this thing is truncating, okay, or I mean the energy cascade still goes all the way up to the smallest wave number. So but still one could come up with a length scale where it starts to go down. So I don't have a hand waving picture also which tells you what is the length scale which gives you this. One can predict what is the length scale for this crossover, and that length scale is similar to the balance of the elastic forces with the viscous forces. And this, I mean, one can come up with a simple expression like polymer viscosity cube divided by polymer dissipation raised to 1/4, and surprisingly that gives very nice cutoff for the scale where this transfer is happening. Okay, but if you want to understand this in one single shot, again we borrow an idea which was earlier proposed by Itamar, is that maybe all this can be understood in terms of some scale dependent effective viscosity. And then the question is that if I come up with some scale dependent effective viscosity expression which gives me how does the energy transfer gets modified, will it be also able to tell me how are the small scale structures are getting modified? So one thing is to say that, oh, I put in some scale dependent effective viscosity and I get back what is the energy spectrum in presence of polymer additives. The other thing is to say that oh, not only I get this, but I am also able to reproduce how the small scale are suppressed in presence of polymers, and I am able to get more or less everything in terms of that scale dependent effective viscosity. So that is what I would, so let me skip, oh no, this I need to talk about. So before we go into that, one thing to note is that if you plot what is the distribution of vortices to strain in two-dimensional turbulent flows, what you find is that this is distribution of vorticity. So when lambda is positive, it's a vortex dominated system. If lambda is negative, it's a strain dominated system. And so if you plot the distribution of lambda, you find it has this behavior, which actually you can theoretically get by assuming that both the vorticity and strain are Gaussian random variables with some spatial correlation, and you plug in some number for the spatial correlation. Not sure how can one predict that number which would give you this exact distribution analytically. Okay, however, what is clear is that when I add polymers to it, this large and the regions of large vorticity and large strain are reduced in presence of polymers. So that's all right, and that one also observes when you look at rate of strain in the system. And then you could look at, if you look at the picture, what you find indeed is that the places where polymers are stretched are in these thin filamentary regimes. So all these regimes where you have an extensional flow, that is where most polymer extension is taking place, and where you have vortices, the polymers would stumble, so there is not much extension. Okay, so the regions where polymers would be affecting the flow are indeed these extensional regions, and which is again consistent with the qualitative picture that one has in mind. Now the question is, can I come up with an effective viscosity which describes not only this picture but also describes this picture? And the answer to that is yes, but I mean the answer I am going to give you is that I am not going to give you a predictive form for the effective viscosity, but I am going to extract the effective viscosity from my simulations and plug it in over here, and then try to see that if I am able to reproduce my simulations with polymers. Okay, and the way to go about it is to say that, well, if there was an effective viscosity, ought to have a form which is some effective viscosity times the gradient of velocity. And the claim is that if the polymer relaxation time is small, this is nothing but as if this is a constant number, and then you go back to the Einsteinian description where you have small sphere, where you have a dispersion of spheres in a liquid, and then you ask what is the effective viscosity of that. So then with this you would have a modified Navier-Stokes equation which looks like this, and let's see what you do. So I mean, in spectral space, if you do all the arithmetic, you would get a form for effective viscosity which is dependent on actually the spectral transfer of or the flux of polymers into the fluid. But let me not go into that, and let me assume that you can define some kind of effective viscosity which has a non-trivial form, of course. The effective viscosity has to be positive at intermediate scale because you want to suck away energy from the fluid, and it has to be negative over here because you are pumping in energy into the fluid. So it has to have this full picture, and the question is, if I plug in this form back into the Navier-Stokes system, what do you get? So the question is, does this form of scale dependent viscosity work? So what I did was, here is the energy for the pure Navier-Stokes simulation. The green curve, the black curve is the simulation with Navier-Stokes with polymer additives, and the green curve is the simulation with the effective viscosity. So you straight away see that this effective viscosity not only, the first thing that it gives, which is heartening, is that it is able to reproduce the energy content which is present in your system. Okay. The second thing it does is that if you look at energy spectrum, again the blue one is the pure Navier-Stokes, the black one is, the green one is Navier-Stokes, sorry, the black one is Navier-Stokes plus polymers, and the green one is again the effective viscosity, and you see all the way up to 10 raised to minus 10, the effective viscosity picture clearly captures the energy transfer also. Okay, so that's really nice. And this we think is some numerical noise that is present. Now the other thing is, does it predict the small scale structures also properly? And the point is, yes, it does. So again, this is the Navier-Stokes, and you have the green colored one is Navier-Stokes plus polymers, and the black one is, the black is Navier-Stokes plus polymer, and the green curve is with the effective viscosity. So with this effective viscosity picture, at least in 2D, not only we are able to get the full how is the energy transfer taking place, but we are also able to get how are the small scale structures modified, which is a higher order statistics. Okay, so and we have also looked at things like flatness and other things which also match. So that's heartening because working with the effective viscosity picture is much more cheaper than working with full Navier-Stokes with polymers. The bottleneck is that we don't still have an analytical expression for a closed form thing. So if you tell me that my concentration is this much, my relaxation time is this much, what is the form of effective viscosity? I don't have that. The only thing that I can tell as of now is that there is a hope that we could have that, and the effective viscosity picture would then completely tell you how is the spectral transfer getting modified in presence of polymers, at least in 2D, and we hope that the same picture would also work in 3D or should work in 3D. So to conclude, what I have shown is that for very different reasons, in two very different systems, although the energy spectrums look very similar, the way or the reasons by which the things are getting modified is different, although the force which is involved in the modification of the spectral transfer is the same, which is the elastic energy contribution, either because of the polymer stretching or recoil, or the surface tension elastic energy contribution because of deformation of interfaces. Okay, and yeah, that's about it. Thank you. Yeah.
There is negative viscosity. How can you justify negative viscosity? Negative viscosity is usually instability. It's not a loud concept, right?
I agree. So, but the way I'm thinking about it is more in the sense of that it's not negative viscosity in real space. So you see, these are the wave number modes which would give you negative. Where the viscosity is going negative.
Assume the number walls, right? Will be boundary.
Yes, yes.
So,
Yeah, that would be all positive. So it's a extra contribution. It's like
it's delta.
It's a delta. Yeah, it's a delta. Yeah, it's a delta. Yeah.
Okay, so it's not really.
No, no, it's a nu plus delta nu. Yeah.
Now, now you don't have walls,
Yeah.
still you can write an equation for the energy flux.
Yes, so that is something that is both for the binary mixtures and for the polymers is something that I want to look at. That what
That may give you a
that would give
drive.
exactly. You're completely right. And in binary mixtures, I have already some results where. So you are completely right. That energy flux is the way to. Yeah, exactly.
Sorry, I just missed something. Could you just show the energy
For polymers or for
for this? Yeah, with polymer, without polymer.
yes.
So, so the thing is that without polymers, you don't see any scaling, and then something like an elastic turbulence thing.
Yes.
You put in a bit of polymers and.
So the two catches. One is that no scaling is something because our Reynolds number were fairly small in the inertial range. Because otherwise you can't explore this region.
Yeah. So now, if I'm thinking of elastic turbulence, is there sort of some observation, etc. I don't remember very well. There's bound on what the spectral slope should be. That is, like
It's around
people
minus
like,
3.
who was it? Professor and others when they did it for 2D, and they had something larger than 3 as well.
So there is large. So okay.
Steinberg's experiment.
Look, I mean, then it's like on a log scale. If I put my line slightly this, I can go from minus 3. Yeah. So it's around minus 3.
That's right. That's the bound.
Yeah. So minus 3 is the bound. Yeah. So this is minus 2.7. Okay. Yeah. No, no, exactly. But I mean, even in any of those things, apart
So
from
again, look at the Lyapunov exponent,
no,
for
no,
example,
no, 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 no.
to actually see whether this is really elastic turbulence or.
Well, that would be a bit difficult to plug out because the point is that it's all mixed up over there. And when you are going to look at Lyapunov exponents, the separation, you are going to calculate them from separation. So to ensure that, I mean, I'm not sure whether, huh? Largest one would give, but what you would get out of. So okay, the question is.
Just to understand whether this is really elastic.
So what then you are asking indirectly the question that if you are over here, no, but then you are asking the question that if you are over here, your Weisenberg number is greater than 1 or not. Is that the question? The scale dependent Weisenberg number is greater than that one can be, yeah. I would expect that would be the case. That I would think would be. I mean, I would. Something that I'm doing right now. Now that's an interesting point because you know at your interface that's like a wall. So you have lots of vorticity production at the wall, and that is again a very interesting. So that's yeah, that's so interesting. I'm looking at.